Welcome to The Explainer. Today, we're going to pull back the curtain on something we do a million times a day, but probably never think about: the incredible, invisible journey your data takes every single time you click a button online.
I mean, really think about it. You click a link, you shoot off an email, you start streaming a show. It feels instant, right? Like it's magic. But it's not magic at all. It's actually a super high-speed, globe-spanning relay race. So come on, let's follow one little piece of your data as it leaves your screen and flies out into the world.
Okay, so let's dive right in. Our whole journey starts right where you are, with the device in your hand or on your desk. This is what's known as the network edge. Yep, your computer, your smartphone, even your smart TV. In internet speak, these are all end systems. And what do you do on them? You run apps. It's those applications, your browser, your email, you name it, that have to send and receive messages. But how do they actually do that? Well, they use something called a socket. The easiest way to think about it is like a doorway. It's the official spot where your app can hand off a message to the network to be sent. It's like the app's personal post office. But before that message goes anywhere, the app has to make a really, really important choice. It has to choose a delivery service. You see, the internet gives you two main options, and honestly, they couldn't be more different in how they operate. On one side, you've got TCP. Think of this as the premium, super careful courier. It establishes a connection first, it guarantees every single piece arrives safely and in the right order, and it even slows down if the network gets jammed up. And then you've got UDP. This is the speedy messenger. No connection, no guarantees, just pure, unadulterated speed. It just throws the data out there and hopes for the best. So it really just comes down to picking the right tool for the right job. For things like email or loading a web page, you absolutely need every single bit of data to show up perfectly, right? You can't have half an email or a website with missing words. That's why they use the Careful Courier TCP. But what about when speed is everything? Think about streaming a movie, playing an online game, or making a video call. A tiny little glitch, a pixel that's off from a millisecond, you'd probably never even notice. But waiting for a perfect redelivery would cause that awful lag and buffering we all hate. For that stuff, you go with the speedy messenger, UDP.
Okay, so our message is all packed up and it has its delivery instructions. Now, it leaves the comfort of your device and plunges into the wild, interconnected heart of the internet, the network core.
You know, the internet doesn't work like an old telephone call where you get one single dedicated line connecting two people. No, it does something way smarter called packet switching. Your whole message gets chopped up into these little chunks called packets, and then each packet is sent off on its own to find its way through the maze of the internet. At every intersection on this journey, a device called a router does this little dance called store and forward. The packet arrives, the router stores it for a split second, checks the address, looks at its map to see the best way to send it, and then whoosh, forwards it to the next stop. This happens over and over, millions of times a second, all across the globe.
But, just like driving on the highway during rush hour, this journey is not always a smooth ride. Oh no. Our tiny packet can run into some serious digital traffic jams and obstacles that can slow it down or even stop it dead in its tracks.
See, at every single router, a packet gets delayed a tiny bit. There's a delay for processing the address, a delay for transmitting it onto the next wire. But the real troublemaker, the total wildcard, is what's called queuing delay. That's the time it spends just waiting in line.
And this really gets to the heart of the problem. When packets start showing up at a router faster than it can send them out, a line starts to form, a queue. And if that line gets too long, if the router's memory, its waiting room, gets totally full, well, sorry, but any new packets that arrive just get dropped. Poof, they're just gone. That's what we call packet loss. So let's just pause and think about this for a second. We have billions of different devices made by thousands of different companies sending trillions of these little packets through this, let's be honest, pretty chaotic network. How on earth does any of this actually work together?
I mean, how does an iPhone made by Apple in Tokyo successfully ask for a web page from a server in Brazil that's running Linux? The answer is both simple and kind of beautiful. Everyone just agrees to play by the same set of rules. A universal rulebook for talking to each other. And this rulebook is structured in layers. This is the absolute secret sauce. Each layer has one very specific job. The application layer just worries about what the message means, like, hey, I'm an email. The transport layer handles how it gets there, reliably with TCP or fast with UDP. The network layer is in charge of global addresses and routing, and the link layer does the physical work of just moving the data to the very next hop. Each layer does its job and trusts the layer below it to do its job. It's a perfect system of organized chaos. So from one little click to a massive global relay race, that's the hidden process that makes our entire digital world possible. We've built this whole thing on a layered rulebook of trust and speed. But as we connect everything from our cars to our coffee makers to this network, you have to ask yourself, how well do we really understand the connection that now runs, well, pretty much everything?
Have you ever stopped, maybe mid-scroll, and wondered what's really going on when you send an email or stream something?
It definitely feels instant, almost like magic.
Exactly, like magic. But today, we're going to pull back that curtain. We're diving deep into the hidden gears of the internet. Our mission, really, is to give you a solid understanding of how our digital world actually talks to itself. From the huge infrastructure down to the tiny data packets.
Right.
We're pulling insights from basically a core university course on this stuff, so hopefully you'll see the internet a bit differently after this.
Well, it's less magic and maybe more. An incredible engineering feat. A really intricate dance happening constantly behind almost everything we do online.
Okay, let's unpack that.
We can start with the basic building block, the fundamentals that make this whole enormous system tick.
Yeah, and enormous is the right word. I mean, people describe the internet as the largest engineered system on Earth. That's mind-boggling.
It is. Billions of computing devices, your phone, my laptop, massive server farms, all connected.
So how do you even begin to manage that scale?
Okay, so at the most basic level, you have these connected devices. We call them hosts, or sometimes end systems.
Like our phones and computers.
Exactly. Your laptop, your smart TV, the server hosting a website you visit. They're the endpoints and what connects them. A whole web of communication links could be fiber optic cables buried underground, could be Wi-Fi signals in your house, copper wires.
All sorts of things.
Right. And crucially, specialized devices called packet switches. Routers are a common type.
Okay, packet switches, what do they do?
When you send data, say, a picture, it doesn't go as one big chunk. It gets broken down into small digital envelopes called packets.
Right, I've heard that term.
And each packet is sort of individually addressed. The switches help guide these packets along a route or path from the source computer to the destination.
Like little digital mail carriers finding their way.
That's a good way to think about it.
Yeah.
And usually your end system connects to all this through an internet service provider, an ISP.
Your Comcast, your Verizon.
Exactly. And for any of this to work, everyone has to follow the same rules. That's where protocols come in. They're the agreed upon standards, the language the devices speak.
So like TCP/IP.
That's a protocol.
That's a major one, yes. Protocols define how messages are formatted, how errors are handled, everything needed for devices to understand each other.
Okay, here's where I think it gets really interesting for, everyday users. This massive system doesn't just sit there. It provides services for our apps, right?
Precisely. For what we call distributed applications.
Meaning?
Apps that aren't just running solely on your phone or computer. Think Netflix, online banking, cloud storage. They involve communication across the network.
So most things we use.
Pretty much. These apps communicate using something called socket interfaces.
Sockets. Like a wall socket.
Kind of. It's the specific point where an application plugs into the network to send or receive data. It's the doorway between the app and the network infrastructure.
Okay.
And data flow can be pushed, where a server sends you info, maybe a notification.
Right. Or pulled, which is more common, where your device, the client, requests data from a server, like loading a web page.
And this push and pull is happening constantly behind the scenes.
Every second you're connected.
So this huge system, how is it structured? You mentioned hosts and switches, but is there a bigger picture?
Yeah, engineers think about it in two main parts, the network edge and the network core.
Edge and core.
Yeah.
Okay, like local versus highway.
That's a decent analogy, actually. The network edge is where we are. It's where the hosts, our computers, phones, run their application programs. acting as clients mostly, or sometimes servers.
Like my web browser is a client.
Exactly. And connecting your device at the edge to the wider internet is what's called an access network.
My home Wi-Fi.
That's part of it. The access network connects your end system to the very first router it encounters on the path outwards. We call that the edge router.
Right.
And the technology for that access can be, well, lots of things. DSL, using phone lines, cable TV lines, fiber to the home.
FTT.
Or increasingly wireless, like 4G, 5G mobile networks.
Right.
Inside your home or office, the local area network, the LAN, usually runs on Ethernet cables or Wi-Fi. And as you hinted, that wireless wide area access is becoming popular, letting us connect from almost anywhere.
Okay, so that's the edge. What about the core, the highway system?
Exactly. The network core is that vast mesh of packet switches and links interconnecting everything. It's the backbone.
Routers and the big cables.
Essentially, yes. Messages travel through this core as those packets we mentioned. And a key thing these core switches do is store and forward.
Store and forward, meaning?
It means a router has to receive the entire packet before it can even start sending it out on the next link in the path.
Okay, so we can't just stream the bits through instantly.
Right. It has to buffer the whole packet first, and this process, while necessary, introduces delays.
Delays, like lag.
Precisely. There are actually 4 main types. First, nodal processing delay, the time the router takes just to examine the packet's header and figure out where to send it next. Second, queuing delay. If the link the packet needs to go out on is busy sending another packet, ours has to wait in line, in a queue.
Like waiting in traffic.
Exactly like traffic. Third is transmission delay. This is the time it actually takes to push all the bits of the packet onto the link. Depends on the packet size and the link's speed.
Makes sense.
And finally, propagation delay. That's just the time it takes for the signal, the electrical pulse or light pulse, to travel physically along the length of the wire or fiber, speed of light stuff, but it adds up over long distances.
Wow, okay. 4 types of delay.
And they all add up. Plus, if those queues get too long, if the router's buffer fills up because traffic is too heavy, then packet loss can occur due to congestion. The router just has to drop incoming packets it has no room for.
And that's when my video call stutters or an image breaks.
That's often the reason, yes. Packet loss.
So with all these packets flying around, potentially getting delayed or dropped, how do they even know where to go in this massive core? It's not just random bouncing, right?
Oh, definitely not. It's highly organized, thanks to routing. Each router maintains what's called a forwarding table.
A map.
Sort of, yeah. It's like a dynamic lookup table. Based on the packet's final destination address, the table tells the router which specific outgoing link to send the packet out on next.
And how does it build that table? The internet changes all the time.
Excellent point. The tables aren't static. There are complex routing protocols running constantly. These are algorithms and communication processes that routers use to talk to each other, share information about network reachability, and collectively build and update those forwarding tables. It's how they figure out the best paths.
So it's dynamic, adapting to changes.
Constantly. It's very different from, say, circuit switching.
What's that?
Think of old-fashioned telephone networks. When you made a call, a dedicated circuit, a specific path with guaranteed resources was set up just for your call for the entire duration. The internet mostly uses packet switching, which is more flexible. Resources aren't reserved. Packets from many different conversations can share the same links. The sharing is often done via multiplexing.
Multiplexing.
Yeah, it's just techniques to allow multiple signals or data streams to share one communication channel, like time division multiplexing, where everyone takes tiny turns using the link, or frequency division, where different conversations use different frequency bands on the same wire. It makes network usage much more efficient.
Got it. Sharing the road, basically.
A good way to put it. And speaking of sharing, how do all the different ISPs connect to each other to form the global internet?
Yeah, how does my local ISP connect to someone's ISP in another country?
It's hierarchical, mostly.
Yeah.
At the top, you have Tier 1 ISPs. These are huge companies that operate massive, high-speed, global backbone networks. Think of them as the intercontinental superhighways.
Okay.
Then, regional ISPs are connected to Tier 1 ISPs. They operate over smaller geographical areas, like states or countries, and connect to one or more Tier 1 providers.
Like on-ramps to the superhighway.
Exactly. And the physical places where these connections happen, where an ISP makes its routers available for others to connect, are called points of presence, or POPs.
POPs? Okay.
Some large customers or smaller ISPs might connect to multiple providers for reliability. That's called multi-homing.
Makes sense. Backup connections.
Right. And sometimes nearby ISPs, maybe competitors in the same city, find it cheaper to connect directly to each other to exchange local traffic rather than sending it up to a tier 1 and back down. They do this at Internet Exchange Points, or IXPs. It saves money and can reduce latency.
So direct connections between networks.
Yep, called peering. And it's not just ISPs. Big content providers have their own networks, too.
Like Google or Netflix?
Exactly. They build out their own global networks to place their servers closer to users, often connecting directly inside ISP facilities or at ISPs, to deliver their video or search results much more efficiently.
Right, bypassing parts of the public internet.
For better performance, yeah.
Okay, so we've got structure, the edge, the core, the connections. But what about the actual experience? What determines if my connection feels fast or slow?
Performance, yeah, that comes down to 3 key metrics: delay, loss, and throughput.
We talked about the 4 types of delay.
Right. Nodal processing, queuing, transmission, and propagation. And just to put a number on transmission delay, if your packet is, say, L bits long, and the link speed is R bits per second, the transmission delay is simply L divided by R LR seconds to push the packet out.
Simple enough.
Now consider traffic intensity. Let's say packets arrive at a router queue at an average rate of A packets per second. The average traffic intensity is often represented as layer.
L times A over R. Okay, what does that tell us?
It's crucial if layer is greater than 1.
Meaning data is arriving faster than the link can send it out.
Exactly. Then the queue grows without bound, theoretically. In reality, router queues are finite. So when the queue is full, arriving packets are dropped. That's packet loss due to congestion, directly linked to traffic intensity exceeding 1 for sustained periods.
Which is bad.
Which is bad for performance. But the good news is that engineers can measure the total end-to-end delay, the sum of all these delays across the path, to diagnose problems.
Okay, delay and loss. What about throughput?
Throughput is simply the rate at which bits are actually successfully transferred between sender and receiver. How fast the data is really getting through.
Is that different from my connection speed? Like what my ISP advertises?
It can be. Throughput can be instantaneous, what you're getting right now, or an average over time. If the throughput you're actually getting is less than what your application needs, that creates a bottleneck.
The bottleneck, right.
It might be your access link, or it might be a congested link somewhere deep in the network core. And remember, it's a shared network. Other traffic from other users sharing the same links can absolutely affect the throughput you experience between your computer and a server.
So my neighbor's streaming 4K could slow down my browsing.
Potentially, yes, if you're sharing bottleneck links somewhere along the path.
This complexity, it makes me wonder why we have layers in the internet protocols. Why not just one big system? What problems did layers solve?
That's a fundamental question about the design, and the answer is complexity management. Imagine trying to solve all the problems of network communication in one go. It's overwhelming.
Like what kind of problems?
Okay, super basic. How does a receiving computer even know when one bit ends and the next one starts in an electrical signal? That requires agreement on encoding.
Okay.
Then, how do you group those bits into meaningful units like bytes or words? That's framing.
Right.
How do computers on the same local network, like your home Wi-Fi, uniquely address each other?
MAC addresses.
Exactly. But what happens when communication goes beyond the local network? Now you need global addressing, like IP addresses, and you need routing to find paths across different networks. And this is where data gets organized into packets.
Okay, so layers handle these different stages.
Precisely. But wait, there's more. When it's not just computers, but specific applications or processes on those computers communicating.
Like my browser talking to a specific web server process.
Yes. You need a way to identify the process on the destination host, not just the host itself. This needs higher-level transport abstractions. We need to establish end-to-end communication between the processes, often using segments as the unit of data at this layer.
Segments, okay. Different from packets.
A transport layer concept, often carried within network layer packets. And finally, at the very top, the applications identify the meaning of the message. Is this chunk of data part of an email, a video frame, a file transfer?
So each layer builds on the one below it, solving a specific part of the problem.
Exactly. It's modular. You can change how routing works without messing up how applications interpret data, or improve Wi-Fi without changing how TCP works. It's genius, really, like building with Legos.
That makes a lot of sense. Okay, so with these layers helping things along, How do the actual applications talk? We hear terms like client-server and PDP.
Those are the two main network application architectures, ways applications are structured to communicate. Client-server is the classic model.
Like visiting a website.
Perfect example. You have a central server, often powerful, that provides a service. Many clients connect to it to use that service. Your browser is the client, the website's machine is the server.
Right.
But for really popular services, a single server machine isn't nearly enough. That's why we have huge data centers housing many hosts working together to act as one logical server, handling millions of clients.
Okay. Scaling up.
Exactly. The other model is P2P, peer-to-peer.
Like BitTorrent back in the day.
That's a well-known example, yes. In P2P, there's generally no single, always-on central server required. Instead, the computers participating the peers provide services directly to each other. They both request and supply data.
So the users are the infrastructure, in a way.
In a way, yes. A big advantage is that P2P systems are often self-scalable. The more users join, the more capacity the system has, because each new peer brings resources.
Interesting trade-off.
It is. Though it's worth noting, even in P2P, for any specific interaction, the peer that initiates the communication is technically the client for that exchange, and the one responding is the server. The roles can shift.
Okay. And you mentioned sockets earlier as the way apps plug into the network. Can we revisit that? How does it actually work?
Sure. The socket is the programming interface, the API between the application and the network. It's what the application developer uses to say, send this data or listen for incoming data.
So how does data sent to a socket know which computer and which application on that computer to go to?
Two key identifiers. First, the IP address. That uniquely identifies the host computer on the entire internet. Think of it like the building's street address. But a computer might be running many network applications at once, a browser, email, a game. So you also need a port number that identifies the specific application or process within that host, like the apartment number in the building.
IP address gets it to the building, port number gets it to the right apartment.
You got it. An IP address plus a port number directs the data to the correct socket on the correct machine. And it's the transport layer protocols, like TCP or UDP, that actually provide the service of delivering data between the correct sockets.
Right, which brings us neatly to the transport layer. You said there are multiple transport layer protocols, and apps choose based on the services required. What services are we talking about?
Well, different apps have very different needs. One key on us is reliable data transfer.
Meaning the data definitely gets there, intact and in order.
Exactly. Guaranteed, error-free, in-sequence delivery. Absolutely critical for things like file transfers, email, financial transactions. You can't afford missing bits.
Makes sense.
But some apps are loss-tolerant. Think live video streaming or online gaming. A tiny glitch, a dropped packet here or there might be acceptable, maybe even preferable to waiting for a retransmission that causes a noticeable pause.
So they don't need perfect reliability.
They prioritize smoothness or real-time speed over perfection. Another service is guaranteed available throughput.
Ensuring a minimum speed.
Yeah, guaranteeing at least a certain data rate. Crucial for bandwidth-sensitive applications like high-def video conferencing. If the rate drops too low, it's unusable.
Right.
But other apps are elastic, like email or basic web browsing. They can adapt and work reasonably well, even if the available bandwidth fluctuates. They'll just take longer if it's slow.
Okay, what else?
Timing. Some applications need guarantees about how long it takes data to get from end to end. Real-time control systems, or maybe very interactive voice calls, have strict end-to-end delay constraints.
Low latency requirements.
Exactly. And finally, a big one today, security using encryption, protecting the data in transit from eavesdropping or tampering. TLS SSL provides this, often working in conjunction with the transport layer.
Okay, let's unpack this more. The two big players in the transport layer are TCP and UDP, right?
Yeah.
How do they fit into these services?
Right. They offer very different service models. Let's start with Transmission Control Protocol, TCP.
The reliable one.
The reliable one, yes. TCP is connection-oriented.
Meaning?
Before any application data flows, TCP on both ends performs a handshaking procedure. They exchange control messages to set up parameters, agree they're ready to communicate, and establish a connection, like making a phone call and saying hello before you start talking.
Okay, establishes a connection first.
Yes, a full duplex connection, meaning data can flow both ways simultaneously, and when they're done, the connection must be torn down explicitly. Right. Its main feature is reliability. TCP acknowledges the delivery of data segments. If the sender doesn't get an acknowledgement back within a certain time, it assumes the segment was lost and resends it. It ensures everything gets there and in the right order.
Okay, reliable, connection-oriented.
Yeah.
What else?
Critically, TCP has congestion control. It tries to be a good network citizen.
How so?
It monitors the network for signs of congestion like lost packets or increasing delays, and if it detects congestion, it will throttle the sending process, slowing down its transmission rate to avoid overwhelming the network further.
So it backs off automatically?
Yes, it tries to match its sending rate to the available capacity.
Okay, that sounds pretty comprehensive. What about the other one, UDP?
User Datagram Protocol, UDP. It's the polar opposite in many ways. Think lightweight with minimal services.
Minimal.
Very minimal. First, it's connectionless. There's no handshaking or negotiations. An application using UDP just fires off data segments whenever it wants.
Just sends it. No setup.
No setup, which also means it's unreliable. There's no guarantee of delivery, no acknowledgments, no retransmissions. Packets might get lost, duplicated, or even arrive out of order, and UDP itself won't do anything about it.
Wow, okay.
It's up to the application using UDP to handle that if it cares. And crucially, UDP has no congestion control.
None at all.
None built in. An application using UDP can, and often will, just pump the packets to the network layer at any rate it chooses, regardless of whether the network is totally overloaded.
That sounds potentially dangerous for the network.
It can be. If many UDP sources blast data without backing off, they can cause severe congestion, impacting everyone, including TCP flows.
So why would anyone use UDP then? It sounds like TCP is just better. Reliable, controlled.
Great question. Because UDP's simplicity and lack of overhead are its strengths for certain applications.
Like what?
Think about those loss-tolerant, timing-sensitive apps. Online gaming, live streaming video, voice over IP.
Yeah.
For those, the slight delay introduced by TCP, waiting for acknowledgments or retransmitting a lost packet, can be worse than just losing a tiny bit of data. A missed voice sample or a slightly glitched video frame is often preferable to a noticeable pause or lag while TCP sorts things out.
So speed and low overhead are the priority.
Exactly. UDP is fast, simple, no connection setup delay, no retransmission delays. You trade reliability and congestion control for speed and responsiveness. So TCP for things where every bit matters and must arrive correctly, web pages, files, email. UDP for things where speed is king and you can tolerate occasional small losses, real-time media, some types of queries like DNS.
That makes perfect sense. Different tools for different jobs. Okay, one last layer then. We've got data moving reliably or not between applications via TCP or UDP. What about the application layer protocols? What's their job at the very top?
They define the actual conversation between applications. Think of HTTP for the web, SMTP for email, FTP for file transfer. These protocols specify exactly how a message is structured, what fields are in an HTTP request, what does an email header look like. They define the type of messages exchanged, like requests and responses.
Got it, the format.
The format, yes, which includes the syntax of the various message types, the exact grammar, if you will. They also define the semantics of the fields, what each part of the message means. And finally, the rules for determining when and how a process sends messages and responds to messages. The flow of the conversation.
So it's the specific language for each type of application interaction.
Precisely. It's an important part of the application itself, enabling meaningful communication on top of the transport services provided by TCP or UDP. It's how your browser and a web server agree on how to ask for and deliver a web page.
Wow. Okay. So from the massive physical network through the core routers, the packet switching, delays, throughput, the layered protocols like TCP and UDP managing reliability and flow, all the way up to the specific application languages. We've covered a lot.
We really have. It's easy to take it for granted, but when you unpack it, the internet is just an incredible system.
It really is. Every click, every stream relies on this hidden, complex dance we've been talking about.
And that layered approach is key. It allows different parts to evolve independently. We get faster Wi-Fi or better routing algorithms or new applications, all fitting together because of that modular design. And the choice between TCP and UDP provides the flexibility needed for the huge variety of things we do online.
Absolutely. It's quite something. So thinking about all this, the structure, the protocols, the constant evolution, here's something to maybe mull over. Given this deep dive into how things work now, what do you think might be the next big fundamental shift in how the internet operates? What could really redefine our digital experiences down the line?
That's a big question. Maybe how we handle the sheer scale of AI traffic? Or perhaps fundamentally new ways of dressing and routing, quantum networking.
Lots to think about. Something for you, our listener, to ponder as well.